we're going to develop the integral test a little bit further, so it will give us more information about a series. Let's start with what the integral test says. Remember, we have already learned that if you have a positive function, which is continuous and decreasing, and we want to understand the behavior of a series, the sum from n equals 1 to infinity of a sub n, where the nth term a sub n is just the value of this function f at the integer n. And if we know that this integral converges, then the series converges. And we even saw that the actual series itself has a sum which is bigger than this integral from 1 to infinity of f of x dx, but that if you take the same series and leave off the first term, the sum from n equals 2 to infinity of a sub n, then what you get is actually less than that integral. Let me remind you of the picture that told us that. We have a decreasing, continuous, and positive function, y equals f of x here to give us this curve. Here we have 1, 2, 3, 4, etc. The height here, the y-coordinate of this point, is exactly a sub 1. So the area of this rectangle is a sub 1. The height of this point here on the graph of f is a sub 2. So the area of this rectangle is a sub 2, since it has width 1 and height a sub 2. And we can continue on like that. A sub 3, a sub 4, etc. And we're going to go all the way to the right. Now, if we cut things off here at x equals 1, the total area under the curve is just this integral from 1 to infinity of f of x dx. And if we assume that that integral converges, that means there's a finite total area under the curve. The sum of a sub 2 plus a sub 3 plus a sub 4, etc., that's this sum on the left, is clearly less than the value of that integral because the area of all of these rectangles geometrically fit inside of this region underneath the curve. So the sum of the areas of those rectangles, in other words, the sum of a sub n from 2 to infinity, will be less than the integral. However, if we consider boxes to the right here, then this bigger box has area a sub 1. A sub 1 for the bigger one. Again, we'll do this, and now we'll have a sub 2. We'll do the box like this, a sub 3, etc. So that if we include that first term, a sub 1, and look at these different rectangles, the sum of the areas of the rectangles is precisely the sum from n equals 1 to infinity of a sub n, and that clearly will be greater than the area underneath the curve, which is the integral from 1 to infinity of f of x dx. This is what the integral test is all about. If we know this integral converges, then so does the sum, and we get this estimate for the size of the sum. Here's another way to write what this tells us about the size of the sum. If we let s be the value of this sum, again, when the integral converges, we know this will be some finite number. Then what this tells us is that s is actually bigger than this integral from 1 to infinity of f of x dx. That's what this right inequality says. The left inequality, the term on the left here is not s, but it's s minus a sub 1, and that's less than the integral of f of x dx. In other words, s is less than this integral plus a sub 1. If I just rewrite these inequalities a slightly different way, we find that the sum s is somewhere between the integral from 1 to infinity of f of x dx and the integral plus a sub 1, the integral from 1 to infinity f of x dx plus a sub 1. So, even though the integral test does not tell us exactly the value of the sum that we wish to find, It does tell us that the sum is somewhere between the value of this integral that we compute and the value of the integral plus a sub 1, the first term of the series. What if we want a better error estimate? What do I mean by that? We want a more accurate estimate for the actual sum S of the series. Well, series are naturally approximable, by which I mean you always have one natural way to approximate the value of an infinite series, and that's to use a partial sum S sub n as an estimate. When you have a convergent series, I'll write that up here, when a series converges, say to S, then the partial sums S sub n as a sequence converge to S. So these terms S sub n, the partial sums, get closer and closer and closer. In fact, they get and stay arbitrarily close to S, so they can be used as a good way to approximate the value of the series itself. If we're going to talk about an approximation, that's only useful if we have some idea how close it is. So we ask the question, how wrong is the nth partial sum if we use that as an estimate for the full sum? So again, if we let S be the full sum of the series, we define R sub n to be S minus S sub n. This is how wrong S sub n is when used to approximate the actual sum S. It's this difference. And when we have a series for which the integral test is applicable, all of the terms are positive because they all have to come from some sort of from some positive function. So this difference, R sub n, which is S minus S sub n, that's just all the terms here in the series which are not included among the first n. That's an plus 1 plus an plus 2. These are the ones we're leaving out when we just use the nth partial sum as an approximation. Our error is this, and this will be positive. In other words, S sub n is an underestimate, and the error, R sub n, is given by this formula. Just a sub n plus 1 plus a sub n plus 2, etc. Now, if we can't compute the exact value of S, we're not going to be able to compute the exact value of the error. But our goal is to somehow use something like the integral test, or a version of the integral test, to approximate R sub n. So how can we use an integral to approximate the size of this error, R sub n, which is a sub n plus 1 plus a sub n plus 2, etc.? Well, I claim that that error, R sub n, is always going to be between the integral from n plus 1 to infinity of f of x dx and n to infinity of f of x dx. And we can see that that's true by drawing a picture that's very similar to the picture we used at first. So let's say we have here a graph y equals f of x. Remember, it has to be a positive, decreasing, continuous function. So 1 might be over here, 2 here, and then we'll just skip ahead. Let's say we have n here, n plus 1 here, n plus 2 here, etc. Now, let's start with the right side here. R sub n, which is the sum of an plus 1 plus an plus 2, etc., can be seen as the sum of the areas of the following rectangles. This y coordinate at this point is a sub n plus 1, and since the base again has width 1, this rectangle has area an plus 1. This rectangle has area a sub n plus 2, etc. So if I add up all the terms an plus 1 plus an plus 2, on and on and on, and get r sub n, that'll be less than the area underneath the graph of f, starting with x equals n and going out to infinity. That's exactly this term here. So that tells us that r sub n is less than this integral from n to infinity of f of x dx. In order to see the other inequality, we can just modify the rectangles a little bit. We see this inequality on the left side here, that r sub n is greater than the integral from n plus 1 to infinity of f of x dx, by considering this picture where we start here at n plus 1 and look at the rectangles to the right. This has area a sub n plus 1 because the y-coordinate of this point on the left is exactly a sub n plus 1. It's f of n plus 1, which is how we define a sub n plus 1. Let me just extend this a little bit. Here's a rectangle whose area is a sub n plus 2 because the height is the value of our function f at n plus 2. And we keep going on like this, an plus 3, etc. And so when we add an plus 1 plus a sub n plus 2 plus a sub n plus 3, etc., that's r sub n, and that's greater than the area underneath the graph of f when we begin at x equals n plus 1. Putting those together, we can tell that the error r sub n is tightly bound between these two integrals. What's usually most important for us is this inequality to the right, because if you give somebody an estimate for the error, what you really care about is the ability to say this error is no bigger than some specified amount, and that would be this integral from n to infinity of f of x dx.